Okay, what's the question? What's the question?
You're closer. Okay, I'm gonna
Oh,
try.
no, you got to write it up on the board. No.
I'll just wait for you. I don't have to write. He was making
Wetting fluid will be water. Non-wetting fluid will be air. So, Yucca Mountain, before it was stopped by the Blue Ribbon panel at the beginning of the Obama administration. When was Obama? 2006. Finished in 16, right? So it would have been 2008. Yeah, you're right. So yeah, the Obama administration in 2008 had a Blue Ribbon Committee that shut down Yucca Mountain. The science questions for Yucca Mountain WERB, when it existed, was that it was the only repository in the world that would have radioactive waste in it which was above boiling, because most of them sit below the groundwater table. Yucca Mountain sits something like 300 meters above the groundwater table at the depth where it would be disposed. But the material within the zones around the caverns or the tunnels is partly saturated to some degree. And so what would happen is that the material there will lose its fluid as it gets heated up. So the kind of bottom line is, if I don't know that I want to go into huge detail. Isn't it due today? Christ. Sorry? Oh, change it. Yeah, I don't mind. So for me, probably Matt doesn't mind. I'd imagine that so long as he has them all by the time he wants to grade them, he doesn't care if it's midnight tonight or 1 o'clock in the morning tomorrow. Joke. I can't use my pen here. So the idea is, so you have, these are horrible real figures of the system. So you have average magnitudes of porosity and saturations. And so if you know the porosity and then know the saturation, then the product of porosity and saturation times the volume of the rock gives you the amount of water that you can drive out if you evaporate it, right? So that would be porosity times the total volume. So it's probably easiest. Very attentive when you're getting something out of it. This immediate gratification. I'm a funny guy. You have to believe that. Hey, we've all been where you are now once. I was a bad undergraduate student. Poor undergraduate student. So the idea, you had this repository. I'll give you an overview. And so the easiest thing to do is to assume that this goes forever, and so you can take a piece of this which is 1 meter by 1 meter by 1 meter. So if you have something that's 1 meter by 1 meter, and these questions were written a long time ago. Am I doing too much? I see you making gesticulations, Miranda.
Yeah, we didn't see anything.
Oh, you don't see anything?
On the screen.
What? I can see it. Oh, that's why. Good. You should shout. Louder. There. So, repository, ground surface. I think this isn't it 300 meters and 300 meters? 300 meters to the water. Because I can't quite remember. I don't look at these every year. It is something like that, right? And this is the water table. So this zone exists. These are what the plots you have of you have, hey, stop giggling. You have plots of porosity and saturation with these. I think, does it say something like it'll dry out to 150 meters above and below? So this dry out zone. So this is roughly 3. And so what you could do is you could take this section and you can calculate the native water that's in here. Come along, girls, ladies. And so you can calculate the volume of water. This is 1 by 1 by 1 by 1. Volume of water equals 1 by 1 by H. That's the volume. Guess we always used to do this, right? Times porosity times saturation of water. So that's the amount of water that's available. So if you evaporate it, it'll go here, and it has a certain height that it can go into. I guess that's probably 150 meters. And the amount of volume that's available for that saturation of water versus PC SNW0. And so when you boil that stuff off, the amount of space that you have to be able to get it in. So if you know what the saturation is in here, the question is how much can you accommodate? And so you can only accommodate this much, right? So you can remove all the water from here because you're boiling it off. It's not limited by irreducible saturations because it's being evaporated. And the space it has to go would be the saturation minus the irreducible saturation of the non-wetting. So it would be something like, bless you. So this length here would be the saturation of water minus the irreducible non-wetting saturation. This is the air that's left in the system when you do it, multiplied by porosity times volume. So that's it. Was this a plan? Devious. Very devious.
I think our confusion came because the formula was
In the notes,
yeah,
in
it
the
was
notes it's
the
reversed,
non-wetting
the non-wetting
minus the
saturation minus the wetting saturation.
and then all
Okay.
the results were negative.
Whose notes are they? Chow Yu Wang's notes? Does it look like my handwriting? No, right?
It's Matt's fault.
They're not my handwriting. Is it neat handwriting?
Yes.
Yeah, it's not mine. So is that's the sticking point? That's the dilemma?
Yep.
Okay. Yeah. It's interesting, I was using my 303 notes today and I noticed something in them that's wrong for this geothermal class that's been there for forever. I guess that's because I write stuff rather than using notes. So, yeah. But yeah, so that's my sense, right? This is the availability of the, this is the saturation where it is. So this is the amounts already in there. This is the amount which you can't fill. So this is the remainder that's there. Okay. Find a group to work with. I saw you chatting. I'm always after the well-being of our class. That's just me. All heart. Okay?
Getting to 6th season.
Pardon?
It's getting into 6th season.
Sixth season? Sixth sense?
Sixth
I-
season.
I know.
Like stick season?
I know.
We're all dying. Do you know the song Stick Season?
No.
Do you listen to Noah Kahan?
Say it again.
Do you listen to Noah Kahan?
What is that?
He's an artist.
No, don't know.
Oh, yeah.
I know the Idols.
I think you'd like him.
The Idol?
Idols.
The Idols is a good
Yeah.
That surprised you. I was looking at the videos for this geothermal class, and I was telling the class that, actually, I guess my son sent me a text or called me up to tell me to look at Tiny Desk concert for the Idols a few years ago. Thought they're quite interesting. From Bristol, I understand, right? So what are we doing now? Am I sending you home and we're going to look at the videos? Too late, it's gone. That chance went. You have to react straight away. You don't want to go home?
Which home are we talking about? Like State College home or like home?
Home? No, State College home. State College home. All right. So we're ready to get going? All right. Well, so what to do? So are you going to be doing your homework for the rest of the day here, or?
Like on campus?
Now, I mean.
Yeah.
What are you doing behind those screens? Are you taking notes?
I'm looking at the notes.
Yeah, cool. All right. Go. It's good to get a bit of banter going. I like it. You probably think it's not good because it's interrupting stuff, but it's actually kind of nice. So, what do we do? Let's do a recap. This is what we did last time. And this will tie everything together. So we can, you know that we can draw capillary pressure versus saturation diagrams on top of each other. These are what they look like. What was green? Non-wetting was green? This handwriting's a bit better. So if you're asked, if you thought those equations were the wrong way around, then you're asking the right questions, so you understand this. Good. And so that's that. And I guess what we did for the other ones was, let me do this. Do some of you use Notability? This same? You do, yeah?
You know, you can draw, like if you draw a box, it'll make a box for you.
You mean like making a circle when you do this?
I see you draw like in the little lines and I just want to make your life easier.
Oh, I think it won't do it. I can't do it fast enough. Okay?
You sure about that?
No, not now. Good, thank you. Very good. All right. Well, it's always a good day when you get up and you learn something. Capillary pressure. What's definition of capillary pressure? Wetting or non-wetting first? Sorry, don't have time to wait. And so velocity of you'll need this for your next, perhaps. Mu2. I can write faster when I'm not saying it at the same time. It's interesting. It's like talking and chewing gum, I guess. Walking and chewing gum. So this is the non-wetting. This is the wetting. And so we can get the velocities of each of these. And so really, you remember, so if I draw a circle, we just split it between the two fluids. Yeah. Is there a quick way to get it to switch colors backwards and forwards by hitting the keyboard? No. I guess the
I
answer.
just tapped the screen. I have undo as my single tap.
But Control Z undoes it. Yeah.
I didn't know that.
Oh yeah, tap screen once. Yeah, with two fingers. Yeah.
Yes.
Control Z does the same thing. All right. So we talked about how to get flow rates. I guess the other thing is that the volumetric flow rate of water would be the velocity times the total area of the flow, total area, not the subsidiary areas. The subsidiary areas are given roughly in the proportions of the saturations. That's all we did. So these are equations you can use. We need to be a bit careful when we use these, because if you're having vertical flow, you have to worry about the unit weight of the fluid. There's an extra term that comes in there. So these are very important relationships for us. This is by definition the capillary pressure at zero saturation of the non-wetting fluid, which we also call the bubbling pressure. This is a drying curve. This is a wetting curve. We have scanning curves as we go across them. And in reality, if we look at these curves, in this, I guess, we have KR2 and KR1. This is the non-wetting, and this is the wetting. You just need to worry about our formalism. These are the places where we can't get to after we've come down. We know that we can always scale capillary pressure. It's sometimes nice slowing things down, bless you, and going in directions. So this would be bless you again. And so this is, by definition, this is capillary pressure. This is the pressure in the wetting fluid. This is the pressure in the non-wetting fluid. Oops. I got little buttons on this keyboard that do Control Z for me. So yeah, by definition, since this is the definition of capillary pressure, as you go above the water table, for instance, this pressure is negative, this pressure is positive. Yeah, this pressure is positive, this negative, so minus minus negative makes this positive. And so it's just the difference between these. We drew it the other way around. And likewise, you can draw it as you go down, but I guess that the only point I'm making is that you can scale this diagram with either capillary pressure or you can scale it with elevation, because capillary pressure is equal to non-wetting minus wetting, which is equal to Z times unit weight of non-wetting minus unit weight of wetting. So, which is what this blue thing is between them. That's it. So, if you understand that and its relevance, I guess that's a big part of this multi-phase portion of the class. It marries the capillary pressure response, which is controlled by interfacial tension. It defines exactly the architecture of where it ends up with the non-wetting fluid invading the big pores first. The first fluid to get into the system goes into the biggest pores, and then the water is left in the small ones by default as it's pushed out. And that controls some of the things we'll look at today. So that's controls, whoops. And so the motion of the fluids is controlled by Darcy's law, written in two phases: a pressure gradient driving a flow, where we use the permeability for the material, which is the same for water, air, NAPL, any Newtonian fluid. For any given course, a single value. It's in meters squared. It's linked to hydraulic conductivity by this relationship, which you've probably used already. Permeability, meters squared. Viscosity, Pascal seconds. Hydraulic conductivity, meters per second. Density, kilograms per meter cubed. And meters squared per second. Meters per second squared. Meters per second squared. Diffusivity is meters squared per second. So you know those. So now, hopefully, you realize why we do this, what we do in 303. It's always a reason to stuff. Never seems so at the time, perhaps. So these controls behavior. So we could use these X relative permeability plots. We tend to not, because the plot, well, actually we tend to. You remember that when we first dealt with this, because we noted that these arrangements of relative areas were really just in proportion to the saturations, if we plotted the saturation against saturation, we had a curve that was just bottom left to top right. I'm going to get rid of these in a minute, and top left to bottom right. But we decided that that's not really tenable because you can't get into these portions here. And so we ignored that. So we thought that might be a good way to do it. And it is a good way to do it. The reality is that behavior is slightly different. And we'll talk about that today. Everyone good with this? Good. I like writing things down. And the reality is that sometimes behavior is a bit different. One nice thing about this is that if you took any portion, if I'm still gray here, and if you calculated the relative perm for the wetting fluid, and you calculated the relative perm for the non-wetting fluid, these two heights, in other words, these would be the relative perms as you go across here. This plus this I won't change the color, KR2 is equal to 1. These would sum to 1, just by the very nature of the fact that they end up in the same place. That happens not to be true, and so perhaps you don't want to, I was thinking of getting rid of this. And so if you look at real curves, we said this last time, lousy figure comes out of Bayer's book, Jacob Bayer's book, for the relative permeability to water, relative permeability to air, non-wetting NAPL. The relative permeability to the non-wetting fluid is higher, is larger. And the reason for that is the same reason that when you have a plug in a Welge apparatus surrounded by oil and you pressurize the oil so it penetrates into the core and pushes brine out of the bottom of the core in that little U-shaped apparatus we talked about, it first of all goes in the non-wetting fluid, which chooses the biggest pores. The biggest pores because the transmission, we'll find out today perhaps, you can write the permeability in terms of a bundle of capillaries. We won't do the derivation, you'll be happy to know. But if you take a bunch of little capillary tubes where you're not looking at the height rise of fluids in the tubes, but you're looking at the transmission of water along those tubes, you can show that the volumetric flow rate to those tubes is proportional to the radius squared, or diameter squared. So the permeability you can write as something like the porosity times the diameter of the pipe divided by 32 or 96 or 64, turns out. And so those different numbers come out depending on whether you draw your system that looks like, we always go down these time warp holes, rabbit holes. I was going to say rat hole. It's not. So this would be 32. If you think of a bundle of capillaries that is arranged like this, going into the page, but also has them going on this side, looks like sponge pens, whoever. This would be 64. And if you had them in all three directions, in the top as well, that's 96. So this is for capillary tubes like this, and like this. And all it's doing is dividing up the porosity for a specimen, which you'd know, and dividing it into these individual tubes. If you have a given porosity and you're dividing it between tubes in three directions, then the diameters of these tubes would be smaller, and so your permeability would be smaller. That's really all it is. So this represents case 1. This represents, I didn't draw it, this would be case 3, if that makes sense. But the point I wanted to make was that permeability is proportional to diameter squared. And so if in the Welge apparatus the non-aqueous fluid goes into the parts of the pore space which are the biggest pores, then those pores automatically would have the biggest permeability. And therefore the biggest relative permeability that you'd measure in those specimens would be the permeability of the largest fraction of the pores, which would be higher. So that's why this is higher than this. So perhaps an esoteric point, but a point nonetheless. Also, you notice that if you add them together, if you add the non-wetting relative perm to the wetting relative perm, that would be these, they don't equal 1. Because that's given by this. Clearly that's not equal to 1 here. And you have to figure out a trajectory and you go through these no-go zones. It could be something. You could imagine it like this, or it could be like this. Doesn't matter. My guess is for all practical purposes you will almost not have these, and you'll have to use something as a first approximation, which would be this, which is perfectly adequate. And that's what we'll use in this class. So that's what real capillary pressure versus saturation curves look like. Also, if they're going, if you're draining the fluid and then imbibing it again, then you'd expect to see the same hysteresis that you see in the capillary pressure versus saturation curves. And they would look like this. The non-wetting one would be higher than the wetting one, wetting fluid, because of what we said before. The hysteresis is because it matters whether it's previously wet or previously dry. The antecedent moisture conditions, I guess, is a fancy way of saying it. And if you end up going backwards in pressures, so this would be changing capillary pressures, right? So in the same way that if you want to switch between these curves here, you're changing capillary pressures by increasing capillary pressure or decreasing capillary pressure. And as a result of that, you get a change in saturation that occurs, like this, right? So in decreasing capillary pressures, bless you, by this amount, it really is cold season, you change saturations. So in this case, you can think of the fact that you're changing a saturation from this point to some other point, because there's no and so you'd imagine that you'd be going down here, like this, right? What's causing it is a change in capillary pressure. Capillary pressure isn't included on the axis of this, so you don't know what it is. But as a result of that capillary pressure change, drop, you're changing saturation. And so if you know the saturation change, you know that as you're going to have to go down and move from this point laterally. Can't move this point laterally above here. You have to be somewhere between these, and so the path it would take be across this. So that would be a scanning curve, and you'd have them in the other directions. Okay? This is saturation of water, 0 to 100, non-wetting the other way. They all come out of Baer's book, actually, Jacob Baer. Don't want to talk about that. All right. We said before that we thought that it was important that the non-aqueous phase liquid would take the superhighways, which are the open pores. And so the biggest pores often in these systems are sometimes fractures. And that was apparent in some of the movies that we kind of looked at, giving cartoons of this. So it might be interesting for us to know what the permeability of a fractured medium is. We just divulged the fact that the permeability of a porous medium can be given by the porosity, the average diameter of the pores, and some factor. I'm going to use 96 again. Sometimes we take, instead of the diameter of the pores, the diameter of the grains as a proxy, because you can get that for sand just by sieving it. And I'm sure you've sieved stuff in, you take mineral processing labs, right? In environmental systems. So you sieve it so you know what the grain size distribution is. And there are more sophisticated ways to do it than this. We can do the same for the permeability of a fracture. We can show by doing the same mental gymnastics that the permeability of a single fracture is proportional to the aperture squared. Actually, we derived this for a duct in 303. Proportional, it's equal to the aperture between the fractures. So you have a fracture, which is two walls, two glass plates in contact. Water flows between them. Often it has some roughness. The water flowing between them would be attached with zero velocity at the wall and maximum velocity in the middle. And so this parabolic distribution of velocities is the fact that it's stuck to the wall and is free to do whatever it wants in the middle. This shape is controlled by the viscosity, etc. And so we can define permeability in terms of this. If we know what the permeability or transmission is within one fracture, what we could do is we could take the number of fractures that we have to be able to describe the permeability per unit width. And so we want to multiply by an area. So these two, So this is a spacing between fractures, which is S, and you can think on the top of this, the repeating That's the height of a fracture. It's not the top of a box. So this depth here. So I'm drawing a section down through here. So the height of the fracture is S. The depth, the height of the aperture, B. And so if you take a repeating unit, each repeating unit starts at the top of the lower fracture and finishes at the top of the upper fracture. A bit of rock, S tall, and a bit of fracture, B tall. And then the next layer cake is on that. That's the repeating feature. So this would be B. And so if you look at the spacing between the number of fractures you get in a meter would be 1 divided by its spacing. So if they're spaced 30 centimeters apart, the number of fractures in a meter would be 3.33, 1 over 0.3. And so you can use this. I'm just going to write it. So the permeability of a fractured medium is equal to B cubed over 12S. That's a 12. And it comes merely from realizing that each of these blocks have a width of width S. And S by S. And in each block we have one fracture which is of width this. So in other words, we note that volumetric flow rate is equal to velocity times area. And so we're just using the area of a fracture and the area of flow. And so this is the permeability of a fracture, a single fracture. This is the permeability, the bulk permeability of the rock. And so you can write it in terms of hydraulic conductivity. So this is a hydraulic conductivity in meters per second. This is a permeability in meters squared. This is length cubed. This is length, so it's meters squared. They're equivalent terms. This is viscosity, kinematic viscosity, which is viscosity divided by density. Because Reynolds number is velocity, density, length divided by viscosity. And so some people take this term out to write Reynolds number as equal to velocity, length divided by kinematic viscosity. Yeah, you don't need to know that. Well, I guess you do if you want to understand this. And so this isn't so useful in that you go in and go down the bypass, 322. It bypasses a city. I don't know that anyone calls it that now. And look at the limestone outcrops, and you see these fractures sitting in there. And so you think you could go there, you could take a feeler gauge that you use to look at the distance between the points on a spark plug, and you could push it in, and you could measure exactly what the separation was between these. I'm not suggesting that you can do that. But what you could do, since permeabilities of fractures are quite tough to get, what you could do instead was that you could measure permeability. So I don't know in 452 if you talked about pump tests. So you can use slug tests or pumping tests to get a magnitude of permeability just by pushing water into the ground at a given pressure and a given rate, which gives you ability to calculate what Darcy's law is for that geometry. We'll talk a bit about it in this class, but not so much. So if you measure K, then you could rearrange this to be able to get the magnitude of the aperture. So if you know what K is, then you could take this expression here and you could rearrange it in terms of aperture. So bulk permeability that you measure, which is equal to B cubed over 12S. If you arrange it in terms of aperture, then it's just bulk permeability times 12S cube root. Now that's what you use it for. And so that's KB, K bulk, bad. 12, that's horrible. I'm just going to write it back, so if you got it. That's beautiful. So pretty. So, the reason is you can measure bulk permeability easily. You can measure the separation between fractures very easily visually in a road cut, or between pieces of core in a borehole, or by using a borehole televiewer to get the magnitude of spacing. And then if you have this, you can get aperture. And if you have aperture, we know that the height rise in a fluid is equal to, is it 2b times unit weight times interfacial tension, I think, for fracture? And isn't it something like HC is equal to 4d over unit weight interfacial tension? So this is for a capillary tube, and this is for a fracture. This is height rise. And so if you can measure permeability very easily, and if you can get spacing very easily, automatically you can get a characteristic of the pore size. And the pore size governs the capillary behavior. So both of these relate somehow to entry pressures, what we call bubbling pressures. Okay? So that's, yes, Miranda.
I could be wrong, but would it not be?
You could be wrong. I'm sure you're not.
Would it not be a cubic root? I don't know if that's.
Yes, thank you. Of course you're not wrong. Cube root for this, yes. So we know that capillary behavior is defined in terms of this. So in the same way that we could think about the capillary, the relative permeability curves that we just talked about for porous media, you could think of fractures as being the same way. These are rough fractures. You could think of these being idealized as a whole bunch of capillary tubes which are together. These capillary tubes have different diameters attached to them. And therefore, since the characteristics of these curves for the non-wetting fluid, it occupies the largest apertures or capillaries first, then you expect it also to have the same kind of characteristics. We can't really tell that from this, but at least we can get one useful parameter potentially out of it. So we can use the same kind of idea to represent those behaviors. Okay, what else? Don't talk about that. All right. Here's actually an interesting summary slide. I'll do this. Yeah, let's do this. I don't have to write now. From 2021, middle of COVID. So you recognize these curves. I don't think we need all this junk that's on it. So you have these curves. I'm not sure they're completely germane to this. What is germane to this is that we have relative permeability curves. They look as whatever they do. They have irreducible saturation portions. But we said that we could write them in terms of capillary pressure versus, or we could convert capillary pressure into some non-dimensionless parameter which we called the Leverett function. And so this J function was the Leverett function. I think double T. And it was a value which has no dimensions. Capillary pressures in units of pressure. Interfacial tensions in units of pressure multiplied by length. Yes, must be. Permeability in terms of meters squared, length squared. Porosity and nothing. Square root of meters squared is length. So Square root of this term here must be in units of length, so this must be also in units of pressure multiplied by length, so it balances out as non-dimensional. But the important thing about this was that we found out that there was a value of this J function, and at the bubbling pressure, then J was equal to 0.3, which seemed like an astounding thing for all the variation that goes on in the subsurface. So we had this revelation that we never really explained. So this is how we might explain it. You don't need all of these, but you need the part that comes below this. This is just summarizing where we've been. Capillary rise in a tube is this. We can define it as a capillary pressure merely by multiplying both sides by unit weight, and we lose the unit weight. Height rise in a fracture is slightly different. Instead of being a diameter, it's an aperture, different term here. Again, we can convert it to a capillary pressure by just multiplying by the unit weight of the fluid that's rising up in here. We've introduced today, I guess this is new, right? The fact that permeabilities for a fracture could be equal to the aperture cubed divided by 12 times the spacing. And we also didn't derive, but we introduced the fact that the permeability could be equal to the pore diameter squared times the porosity and divided by 96 or 32 or 64. But let's choose 96 because it comes out right that way. Relative permeabilities are just a way of scaling the actual permeability from 0 to 1. And they define really an effective permeability, which is just the permeability, relative permeability, which is a function of saturation. Whatever value you have of relative permeability is a function of saturation. That's all I'm saying here. And that if we have that, we can calculate the volumetric flow rate by using the total cross-sectional area, the relative permeability of fluid I, the saturation of fluid I, the viscosity of fluid I, and the pressure gradient. This permeability is always the permeability of the porous medium. So that's kind of a tin pot summary of where we are. But it's always kind of curious, the fact that this term works out to be a J factor, which is 0.3. And the utility of that is that if we know that this bubbling pressure, so at PC0, or the bubbling pressure, then we know that J is equal to 0.3, which is just this intercept on this vertical axis here, which is equal to capillary pressure, interfacial tension, permeability, and porosity. Square root. And so if we did, as we said before, maybe we can evaluate easily the permeability, the porosity. We know that this is a material property you can get from a reference text, interfacial tension. So the only parameter we don't have is this. And so if we immediately know that this is the case, then we can calculate what the bubbling pressure is. So immediately, if you know your capillary pressure curve is going to look something like this, you can scale it to this. And we have scaled curves for this in terms of J. And so if you get this value from the field, you can immediately scale everything to be able to do all your calculations for how saturation, for instance, would change with depth. Because we can also relate capillary pressure to a depth, to Z. Okay? And so this is it here. So we've said that we've have the height rise in the capillary as this. We know that the permeability is also defined commonly in terms of the magnitudes of this characteristic length, the diameter of the pipe tube. So what we could do is we could write this out separately. We could rearrange them, since they both have diameters in them, we could rearrange them. So take this and write it in terms of D, take this and write it in terms of D. We have these two relationships here. If we equate them to each other, we have this. square root 96 is 10, right? Square root 100 is 10. And if you divide both sides through by 10, then, and if you multiply both sides by PC over sigma, PC over sigma, then you get this. That's where it comes from. So the relationships that we looked at in terms of capillary rise aren't really much use to us now, because we know that we'd much prefer to get a real capillary pressure curve from this, because this is the real behavior. So this doesn't help us much. But the utility of being able to link these behaviors to a fundamental characteristic length, which is a permeability, which exists in these, because we've basically got rid of this D, because it controls capillary rise and it also controls permeability. Since it occurs in both equations, we can write them in terms of D and it factors out. So now we can always get the magnitude of this bubbling pressure. If we know the permeability, and if we have that bubbling pressure, we know that we can start constructing these curves, and it means that we could perhaps construct the architecture of these red smeared zones as you go down, up and down through the column that we showed in these cartoons. And that's kind of it. Yeah, that's all I wanted to talk about today, I think. When do we finish? 1:50, all kinds of time. Everyone got that? Let's actually spend the rest of the other time to just whistle through and finish off this very quickly. I know I get your hopes up just to dash them. You're actually getting out of here early. Cruel. Builds character, though. What do we write? Anyone remember this? So maybe you remember, yeah, hopefully you remember this, right? This conservation of mass. So mass flow rate plus rho dV. You'll never need to use what we're talking about now, but it's a big picture. dt. So it's differentiating by parts. Sign convention we applied to this was mass flow rates out or positive, in or negative because of the unit normal. This is the density times the volume is the mass that's present in a control volume, and that if more goes in than goes out, then it has to accumulate. And it accumulates either by increasing the volume of the control volume or changing the density inside it. So increasing the volume of the control volume is a balloon that inflates. Increasing the density inside a set tank would be pumping up a tire. A tire gets bigger. And so that's conservation of mass. If you do that for a system that is the dreaded cube, which is dx by dy by dz. So this is the control volume that you're doing this balance on. Then you end up with an expression like this. This is mass flow rate in, this is the velocity of flow This is the density of the fluid that's going in there. So this is the mass flow rate, in versus out, bless you. And this is, well, you recognize it, of course. This is d dt, porosity, saturation, and density. Whoops. So these are all things that can change. If we have a rigid porous medium, then this can't change. So I won't get rid of it, but n stays constant. If we have liquid filling up a porous medium, then the pores aren't all filled, they're filled with water. So the fluid that goes in there won't change density because the pressure's not changing very much. But what it will do is it'll change the saturation. Instead of being 10% saturated with water, it'll be 20 or 30 or 40. And so this is the accumulation term, which is built up inside a block of rock, which has pores only. And those pores will saturate by increasing the magnitude of this as you put more water into it. And so if you put more water into this cube than you take out, then the only way it can accommodate it is by the saturation increasing. So what we do is we take a cube of rock and we write these equations. And so for multiphase flow, we write equations. We can get one conservation equation for the water. So we write it for the water. We can do the same for the non-wetting fluid. So if you look at these, all I've done is here, I've put in Darcy's law, which is the flow rate is equal to the relative permeability times the permeability over the viscosity times the pressure gradient. So put that in there. That's what this term is here. We're going to ignore the fact that we have this extra term called the swimming pool effect. By putting this just is the term, this is the mass accumulation term for water. Sorry, this is the in versus out term for water. This is the mass accumulation term. We've said the density doesn't change, the porosity doesn't change. The only thing that can change is the saturation. We have density on both sides, so we've taken this density out, and we've taken the density out that exists here. That's why it doesn't exist in this. This is pressure, not density. And so this expression is just conservation. We have conservation of mass for the non-wetting phase, right? So we have a volume, if you centrifuge it down, then you have the volume of solid, you have the volume of wetting fluid, device battery. That's strange because I charged it up, perhaps it's. So that's what it looks like. This doesn't change, is what we're saying. The same density overall in every single one of these because the porosity is not changing. But if the volume in the wetting phase increases, then the volume in the non-wetting phase decreases because saturation 1 plus saturation 2 have to sum up to 1. If one goes up, the other goes down. And so we can write an equation to conserve the non-wetting fluid, which is this. So we've written it in terms of properties. So now we need to figure out whether we can solve it. We have an unknown pressure in the water. We have an unknown saturation of the water. We have an unknown pressure in the non-wetting fluid, air if it's air, and we have an unknown saturation. So we have 2 equations and 4 unknowns. So we have to close a set of equations by doing something. We know that if we sum the saturations, that gives us this constraint here. That's 3 equations and 4 unknowns. And we know that we have a capillary pressure versus saturation curve. So this is this. This is just saying that at every capillary pressure, we have a unique saturation. Well, we know that's not true actually because we perhaps have ambiguity. But essentially we have, if we had a single curve, we'd have unambiguous. So this would be 4 equations, 4 unknowns, and you solve it. We're not going to try solving in this class, but just realize that we can solve it. And if you wanted to do that, then this is what it looked like. This is it. This is conservation of mass for the water. Sorry, mass in equals mass. Yeah, this is conservation of mass for water, conservation mass for the non-wetting, the closure for saturations, capillary pressures. So this is SW plus SNW equals 1. I'm not sure how to explain it. This is the capillary pressure versus saturation curve. And if we put Darcy's law into here and Darcy's law into here, we end up with exactly the same equations we had on the previous sheet, and we can solve them. If we solve them for a very simple geometry that looks like this, you can imagine taking an oil reservoir, as this was originally developed for, or it could be a DNAPL contaminated site, and say you start pumping water into this end of the system. What you'd expect to see is that you start off with an initial saturation of oil in the system, and that the saturation of water increases as it goes along here. So if you look at a section that goes along this length, X, then that's what's kind of shown here. So this length here is this length along here. So what's going to happen? You start off at the irreducible saturation of water. You have this much water in it, and you have this much non-wetting fluid in it. Right? And that case is all the way along the reservoir. That's what it is. So it'll be a little bit of water sitting in a whole bunch of oil, an oil reservoir. You know how the water is held. It's pendular saturation. It's going to be this donut that goes around the grain-to-grain contacts, and a monomolecular film on the grains. And so once you start pumping water into this end, then you'd expect that the saturation of water would increase. The maximum it can increase to is the irreducible saturation of the non-wetting fluid. So this can be 1 minus irreducible saturation of the non-wetting fluid. This is NAPL that's left here, so I guess this is always going to be our green. And progressively, as you put more water in, you get a tongue of water that does this, and then it advances a bit more, and then it advances some more. And then it behaves some strange way which isn't real, but the solution gives you that. So you end up with something like this. So this ends up being water saturation, and this ends up being NAPL saturation in the system. And so now this is taking advantage of the fact that we have all the tools at our disposal. We have some relationship that links capillary pressures to saturation, saturation curves. We have the fact that saturations have to add to 1 because it's a closed volume. And we have the rates at which fluid can make its way in the system is driven by pressures, gradients of pressure. And if you lump that all together as a recipe and try and get a solution, you get something that allows you to be able to calculate how long and in what form the saturations will change to get to some final condition that you want. That's it. And I won't go through the other one because I don't feel like it. But I will say that one of your assignments to do, I think it may be assignment number 4, is to start off with a NAPL plug in a core. So maybe this is saturation of the non-wetting fluid is 10%. I think it is actually 10%. And the question is, if you pump water through this at some volumetric flow rate, how long does it take for you to dissolve this and move it out of the core? The rate at which it goes through there is going to be controlled by the pressure gradient along the length, dP dx, and you know the transmission through the system is going to be given by the rel perm curves, right? So in this particular case, the curve of interest, actually the curve of interest would be water, right? Saturation of water. This would be the water curve. This would be relative permeability to water. And so if you start off at saturation of the napple at 10%, let's say it's 30%, because it makes it more exciting. That means the napple saturation 0 to 1 is 30%. So as you start dissolving stuff through here, you change the saturation of this by going in this direction, reduce it, and so you go up the relative perm curve, and you can calculate the velocity is equal to kr1 over mu1 k dp dx. Did you know this trick? Oh, do you know that one?
Yeah.
Oh, you do.
You can also translate it to text.
Yes.
It doesn't like my handwriting.
Yeah, probably doesn't like mine. So yeah, so you have everything now you know to be able to do this, and this is a little example, a numerical model doing exactly the same thing. But you can do this. All the questions we do in this class are what I would call back of the envelope calculations. Do it within a single page very easily. So good to have that skill. You go into design offices, they'll make you use models to do things. And if you don't know what to expect from the model by being able to do a simple calculation, then sometimes you can get in a lot of trouble. So I think this is a good way to go.